with the non-stationary time series analysis with modern signal processing techniques. And today we'll talk about some applications of the algorithm concepts that we discussed last time. And here is the YouTube video you can find for some more details about ConceFT. I will do some very quick review about what ConceFT is. So the idea of ConceFT is actually trying to handle heavy noise when we apply nonlinear type time frequency analysis like synchrosqueezing. And the basic idea is you can try to find different windows and use windows to estimate the spectrum. And ideally, if you have different orthogonal windows, then the noise after the window function will become independent. And so if you take average, then ideally you will get something that is less noisy. So that is the overall idea. And here is a very nice textbook which you can check. And this multi-taper idea was introduced back in 1982. I remember that is by Thomson, 1982. Yeah. Okay, and this multi-tapering idea was introduced or generalized to the time frequency analysis framework back in 1990 something, I forgot. Okay, but by Patrick Flandrin and his student. The basic idea was very simple. Again, you still use multiple orthogonal windows. For example, here you take 3 different windows and they are orthogonal to each other. And you evaluate, for example, here is synchrosqueezing. And you can see that these 3 plots, they have quite well similar, different time frequency representations. But you can see something in common. That is, there is a curve, right? This curve looks similar, but if you pay attention to the background noise, you will see the background noises will have slightly different behavior. So you just focus on the similarity and the dissimilarity and take average. That is the multi-taper time frequency analysis. If you compare this time frequency analysis with all these 3, you can see that the background is slightly better, and you can still get the main information you have interest. Okay, very good. So that is the multi-taper in time frequency analysis. But because of the main limitations, the Nystrom limitation in time frequency analysis that we discussed in the previous lecture in ConceFT, well, you cannot have too many such windows so that you can do multi-taper. So a very basic idea in ConceFT is, how about if we take all these linear combinations? For example, you can combine H1 and the H2 so that you get something is different from H1, different from H2, but it has some kind of still a window-head behavior. And we collect all these possible windows, and you can say, oh, each window is actually attached to one point in a sphere. Then what can we do? The basic idea of ConceFT is, yes, you can do something, and actually quite a lot. You can take all possible linear combinations. For example, this is R11, H1 plus R12, H2 plus R13, H3. This is the window. This is another window. You see these windows are different. And the resulting time frequency analysis representations are different. And you get a lot. You can get a lot. As many as you wish. And then you take average. And this is the result. Okay, so that is the concept. Which, if you compare with the ground truth, you see the ground truth instantaneous frequency somehow is very well recovered, and the background noise is somehow being suppressed compared with all the other single window time frequency analysis. So that is the idea or the algorithm of ConceFT. The basic idea is a combination or a combination of the nonlinearity of synchrosqueezing and multi-tapering. That is, which we can show is that synchrosqueezing will help you to somehow make the noise less dependent compared with short-time Fourier transform and so on, so that in the end, you will be able to cancel the noise. Okay, so today we will focus on one application of ConceFT. And the application will be EEG analysis. If you remember last time, we talked about some applications of ConceFT to the heart rate variability analysis. And today let's consider electroencephalograph analysis. And we will focus on spindle. So the ultimate goal is to do this kind of long-term monitoring of sleep. Okay, but that is ultimate goal. To do this, we need to have a better understanding of the signals we can collect and so on and so forth, so that we can hopefully achieve our goal. And the focus today will be this kind of EEG signal. This is an EEG signal recorded from the central part of your brain. And experts in EEG analysis, they have collected a lot of facts, saying that, oh, you see, look, there will be something oscillatory here, right? There is another thing oscillatory there, and there. And they say, oh, if the oscillation is roughly 11 hertz to 15 hertz, or 10 to 16 hertz, depending on application, depending on definition, if they see this kind of very frequent, okay, very regular oscillation, then they call it spindle. And this is a very typical feature when you are sleeping in a deep stage. For example, deep sleep stage during N2, then you can see a very clear and obvious spindle, and that is spindle. If we zoom in, that is what we get. If you zoom in this period, okay, and the black curve is the raw EEG signal, and the red one is actually the reconstructed component. Then you apply the reconstruction formula from synchrosqueezing. Then you will see that, hey, there is a kind of oscillation that is very clear, right? And in addition to the oscillation, if you pay attention to the cycle-to-cycle period, then you will see that in the beginning, the cycle-to-cycle period is roughly 81 milliseconds. But in the end, it is roughly 7370 milliseconds, which means the frequency actually increases. The frequency increases because the period decreases. What does this suggest? It suggests that the spindle, although by definition, people say it has frequencies like 12 to 15 hertz or 11 to 15 hertz, but what does it really mean? Okay, in the end, it is kind of time-varying frequency feature, or in the sleep literature, people call it accelerated frequency or decelerated frequency, and we want to quantify it. So now, to quantify this kind of business, you know that what we can do is we apply short-time Fourier transform and show the spectrogram. That's what you can do. And this is the result of ConceFT. And if you pay attention, I have some arrows here. First, if you look at this block, you will see that, oh, it's kind of very obvious. You can see something oscillating around this frequency, but it is kind of spreading and so on. But this spreading is somehow concentrated or enhanced by contrast by ConceFT. First, and if you pay attention, each one has this property, right? And that is what we saw before. The frequency increases. The frequency increases, or you have accelerated frequency. Moreover, you will see that in the low frequency region, which people usually call it delta band means from 0.5 to 4 hertz. You see there will be some kind of, well, spreading and so on. And that spreading is somehow suppressed by ConceFT, so that you can have a more dedicated and concentrated information about the spectral content of the EEG signal. You can also pay attention or do some comparison with the traditional synchrosqueezing that you learned before. Then what you see is the kind of the benefit. And what is the benefit? For example, here, You see, synchrosqueezing is more concentrated because it only uses one window. But it is slightly spreading, but this spreading is somehow accepted. Here, you can still see the frequency tracing and so on. Low frequency region is suppressed likewise. But what is the benefit? If you pay attention to the background, in synchrosqueezing you see there are some strange speckling, and you may ask, okay, is this a signal? Is this a signal? Is this a signal? Well, it's hard to say because it is kind of a random, right? You have EEG signal, and the EEG signal beside the spindle behaves like a random process. And this random process, which means it is random, so it can appear everywhere, just like noise. But ConceFT helps us to suppress those, well, noisy-like behavior, so that you have a more confident, which is a statistical term, and we will come back to this statistical term in the future, but you have a more confident statement to say, hey, this is actually a noise. This is actually a noise. And this is also a noise. But this guy is not a noise. Okay, so it can help us to do so. And moreover, in addition to what I showed you about the low frequency components, it actually has another benefit that can help us to enhance or to reduce the impact of cardiogenic artifacts. If you read the EEG signal on the right-hand side, you may see, hey, there is a spike, right? A spike, a spike, a spike. And if you pay attention, those spikes are actually quite regular. And those spikes come from cardiogenic artifact. That is, you put an EEG sensor on your scalp, but because your heart is beating, there will be hemodynamics. So the recording will sometimes capture that kind of hemodynamics. And those hemodynamics, if you pay attention to short-time Fourier transform, they are actually quite obvious, right? And that may cause troubles when you analyze EEG signal. But in ConceFT, because we have enhanced the main information, so those kind of cardiogenic artifacts are somehow better suppressed, although here you can still see something, but it is less kind of dominant. And on the left-hand side, you can see here, right? It's hard to say if there is a cardiogenic. It is hard to say if there is a spindle or not. But experts told us, hey, there is a spindle. There is experts annotation, and you can see it in ConceFT. So ConceFT helps us to enhance the contrast so that we can see the information we have interest. So with this property, we proposed an algorithm to automatically detect sleep spindle just from a long recording EEG signals. And the algorithm is kind of, well, looks at many steps, but the basic idea is very simple. We'll try to extract different spectral bands information according to time, but when we define the energy, when we define the spectrum, we use the ConceFT instead of the traditional short-time Fourier transform or synchrosqueezing. And once we get all the information we have interest, then we will define some kind of threshold that we learn from the data or experts label, and determine the final locations of sleep spindles. And with that kind of procedure, which is actually very simple, if you go to the literature, the paper in archive, which I should have, I don't the citation, but anyways, you can easily find it using ConceFT and the spindle, and use my name. You can Google and find it. And this is the final result, which we have two publicly available databases, a benchmark, and we compare with two different algorithms, two algorithms. One is A7, one is Sumo. A7 is the best deep learning based algorithm we know so far, and the Sumo is the best deep learning based algorithm we know so far. And if you compare with those algorithms, and you can see that actually using ConceFT to automatically determine spindles, actually the overall accuracy, like sensitivity, precision, and F1 are actually quite nice. So it has this kind of potential. And the final question we want to ask is, in the literature, sleep experts always say, oh, the spindles will have accelerating frequency or decelerating frequency or so on, or called chirp. But the question is the instantaneous frequency really a linear chirp? Or actually if the frequency is time varying or is nonlinear? So what we did was, from the database, we have experts label. And from experts label, we know the location, okay, of the spindle. And then we just fit a curve, use ridge extraction to fit a curve over the experts label. So you can already see from here that we may sometimes have troubles about so-called experts labels. For example, here, very obviously, before experts label, there is a period that has oscillation over this frequency. But should we call this a spindle? Will the spindle of this length or of this length? Experts told us it is of this length, but from time frequency representation, we analyzed it should be of this location. So it is kind of, most of the time, difficult to argue because experts and notation nowadays depends on the signal itself in time domain. So, well, and it is, well, not really that easy to change the society right now, but this is an evidence that maybe something could be considered to improve the label. And if we use experts label to estimate the instantaneous frequency, then you can see something quite interesting. Actually, most of the frequency, instantaneous frequency, decreases. Okay, and the decreases actually have some kind of nonlinearity behavior. And what I did here is, I get all the spindles, and I have all the instantaneous frequencies. I put all of them as the gray curves in the background, and then I draw the mean, which is a black curve of all all spindles instantaneous frequencies, and the blue curves will be the plus and minus standard deviation. Okay, and there is a red dash curve. This red dash curve is actually I fit a quadratic polynomial into it. And from here, you can see that, oh, there is actually some kind of interesting quadratic behavior that fits the signal, the instantaneous frequency. And you can further explore the relationship in between different parameters. For example, this is the top three is from the Dream database. The bottom one is from the mass database. And here what I show you is, this is gamma 0 and the gamma 1. This is I fit a linear curve. And you can see there is a kind of some relationship. It's not guaranteed that the slope is positive or negative. It can be either positive or negative. But if you fit a quadratic polynomial, this is the linear term. Sorry, this is constant term. This is the linear term. Then you can see, okay, there's still some kind of behavior. But if you look at the linear chirp and the quadratic chirp, then you will see that seems to have some kind of interesting behavior relationship in between the frequency. But what does it mean? We don't know. That is something we are talking to experts, and hopefully we can get some further analysis. And the spindle actually plays a very critical and important role in EEG analysis.